The Merlin 1D has flown over 400 missions, failure rate under 0.5%. That's the kind of flight heritage that lets engineers truly understand how an engine works. And more importantly, how it fails. Every methane engine currently flying in the world, combined, hasn't reached that number. Meanwhile, SpaceX, Blue Origin, Ariane Group, and Rocket Lab are all betting their next-generation rockets on methane simultaneously, right now. Methane offers better ISP, cleaner combustion, and can be synthesized on Mars. Those are completely valid engineering arguments. But there's a question almost no one is asking directly. Do we actually understand how methane fails yet? The answer will change how you read every piece of news about methane engines from here on out. To understand why the flight heritage question matters this much, you first need to understand why methane was chosen in the first place. This wasn't an impulsive call. It's the result of three very specific technical reasons, and all three come from physics, not marketing. Reason 1. Fuel efficiency. In rocket engineering, the measure of an engine's efficiency is called specific impulse, or ISP. Think of it as the miles per gallon of rocketry, except instead of measuring distance per gallon of fuel, it measures the thrust generated per kilogram of propellant consumed per second. Higher ISP means a more efficient engine, and every additional second of ISP means more payload capacity, or less propellant, burned for the same trajectory. The Merlin 1D, running on RP-1, a refined kerosene, achieves roughly 311 seconds of ISP at sea level. That's already strong for an RP-1 engine. SpaceX's Raptor, running on methane, hits approximately 363 seconds at sea level and around 380 seconds in vacuum. A 50 to 70 second ISP delta sounds marginal, but inside the rocket equation, the mathematical relationship between propellant mass and delta V, that difference compounds exponentially. Same propellant load, a methane engine delivers significantly more payload to orbit, or pushes the same payload much farther. Blue Origin's BE-4 sits at roughly 331 seconds at sea level, below Raptor, but still well above legacy RP-1 engines, and compensates with exceptional thrust, approximately 2.4 meganewtons per engine. For context, a single Merlin 1D generates roughly 0.93 meganewtons. The BE-4 is nearly 3 times more powerful per unit. Reason 2. Reusability and maintenance economics. This is the argument fewer people talk about. But in the economics of the launch industry, it may actually matter more than ISP. RP-1 is refined kerosene. It burns efficiently, but it leaves carbon deposits inside the combustion chamber and propellant feed lines. After every flight, a Falcon 9 booster needs careful inspection, and the Merlin engines need to be scrubbed of those deposits before the vehicle flies again. That's time and labor. SpaceX has optimized this process remarkably, turnaround in a matter of weeks. But carbon buildup is a fundamental property of RP-1 that can't be fully engineered away. Methane burns dramatically cleaner. No equivalent carbon fouling. In theory, this means methane engines can be reused faster with less maintenance overhead between flights. That's the direct technical case for methane in next-generation reusable systems. If you want to fly a rocket 10, 50, or 100 times, the inter-flight maintenance cost carries more weight than initial production cost. Methane reduces that cost in theory, though in practice the operational data is still accumulating. Reason 3. Mars. This is the argument SpaceX stated explicitly when designing Starship and Raptor, and it represents a fundamentally different strategic framework from the two above. Mars's atmosphere is approximately 95% CO2. Water, in the form of ice, exists at both poles and in the Martian regolith. Given sufficient power, solar or nuclear, you can run the Sabatier reaction. CO2 plus H2 yields methane and water. That water can then be electrolyzed into H2 and O2, oxygen for breathing, hydrogen to feed back into the Sabatier reaction, and liquid oxygen as oxidizer. Simply put, methane is the only propellant among practical current options that can be manufactured in situ on Mars from available resources. A methane-fueled spacecraft can land on Mars, refuel from local resources, and fly back to Earth, instead of carrying the full return trip propellant from Earth. In the economics and logistics of deep space exploration, that's the difference between feasible and not feasible. These three arguments, better ISP, reusability economics, and in situ resource utilization, form a technically compelling case for methane. That's why it's not just SpaceX and Blue Origin, but also Ariane Group with the Prometheus engine under development for the Themis demonstrator, and Rocket Lab with the REM-75 for Neutron, all moving in the same direction. But there's a problem, and it doesn't live in theory. The flight heritage gap, the number nobody's counting. When an engineer calls an engine reliable, they're not just saying it worked. They're saying it has flown enough times, across enough varied conditions, that we've begun to understand how it fails, and why. That's what flight heritage means, and it's fundamentally different from has successfully flown. Think of it this way: you buy a brand new car and drive it 60 miles without issues. You can say it runs fine, but you can't say you know where it'll break after 125,000 miles, or which component will be the first to go as it ages. For that, you need data from millions of vehicles over millions of miles across many years. Rocket flight heritage operates on the same logic, but with far higher stakes, and no way to gather data by simply waiting. The Merlin 1D has flown over 400 missions since its debut in 2013. Per data from NASA spaceflight.com and SpaceX official updates, Merlin's failure rate is estimated below 0.5%. That number didn't come from good design alone. It came from hundreds of flights accumulating data on real-world behavior, small anomalies detected and fixed, component wear patterns observed and corrected. Merlin is an engine SpaceX understands deeply, not because they're smarter than anyone else, but because they've had enough time and enough flights to learn. The RD-180, the Russian engine powering Atlas V, has over 90 successful launches. It was developed in the 1990s with heritage tracing back to Soviet-era engines and is widely considered one of the most reliable RP-1 engines ever built. That reliability wasn't accidental either. It's the product of decades of operation and learning from the field. Now look at methane engines. SpaceX's Raptor is the most flown methane engine in the world right now. SpaceX doesn't publish engine-level flight counts, but based on Starship flight test data tracked by NASA spaceflight.com and Everyday Astronaut, Raptor is actively accumulating flight data, but still well short of Merlin's 400-plus mission baseline. More critically, Raptor remains in a phase of intensive development, with substantial design changes between versions, from Raptor 1 to Raptor 2 to the current Raptor 3. Each major design revision effectively resets part of the flight heritage clock, because Raptor 2's failure modes don't map cleanly onto Raptor 1's. Blue Origin's BE-4 has even more limited flight heritage. The engine spent over a decade in development, starting around 2012 before its first flight. New Glenn launched in early 2025, and the pre-incident flight count was insufficient to establish a meaningful MTBF, mean time between failures. MTBF isn't a number you extract from a few dozen test runs. It requires hundreds of data points under operational conditions. That's the flight heritage gap. And it's not a Blue Origin or SpaceX problem specifically, it's an industry-wide problem. Every major player is transitioning simultaneously to a propellant whose total accumulated flight heritage across all methane engines worldwide still falls short of what Merlin logs in a single, normal year of operations. Ariane Group's Prometheus, in development for the Themis demonstrator, has 0 flights. Rocket Lab's RE-M-75 for Neutron is still in development. The entire industry is betting on a propellant with a collectively thin flight record. And this leads to a deeper question. Not which methane engine is better, but do we actually understand at scale how methane fails? To answer that, you need to understand why methane produces physically distinct failure modes. How methane fails differently from RP1. 3 critical physical properties. When an engineer says methane and RP1 have different failure modes, That's not a vague observation. It's a direct consequence of three specific physical properties of methane, and understanding them is the key to understanding why flight heritage from RP1 engines simply cannot be transferred to methane. Property 1. Lower density and more complex sloshing behavior. Liquid methane has a density of approximately 422 kilograms per cubic meter. RP1 sits at around 800 kilograms per cubic meter, nearly double. To carry the same energy content, a methane tank needs roughly twice the volume of an equivalent RP1 tank. Why does this matter for failure modes? Picture a large container of water being shaken hard. The liquid mass inside oscillates. That's sloshing. In a flying rocket, sloshing is a serious problem. It generates asymmetric forces, shifts the vehicle's center of mass, and disrupts stability. If the liquid mass oscillates with sufficient amplitude and frequency, it can cause a loss of vehicle control or trigger sudden pressure spikes in the propellant feed lines upstream of the engine. A larger methane tank means a larger liquid mass, and the sloshing dynamics of a larger liquid volume in a larger tank are fundamentally different from what engineers learned working with RP1. Baffles, the internal dividers designed to suppress sloshing, must be designed and calculated from scratch. And critically, sloshing behavior during complex flight phases, like the super heavy boost back burn or a throttle-intensive landing burn, can only be fully validated in actual flight conditions. Per technical analysis cited by NASA spaceflight.com from contributor Chameleon Circuit, the current super heavy booster shows no evidence of baffling to limit LOX, sloshing between engines, a factor that may contribute to certain observed failure modes, though SpaceX has not officially confirmed this assessment. Property 2. More complex cryogenic behavior within the vehicle. Liquid methane has a boiling point of minus 161 degrees Celsius. That's extremely cold, but still warmer than LOX, liquid oxygen, at minus 183 degrees Celsius. When both propellants coexist in a vehicle, you're managing a thermal gradient between two cryogenic fluids simultaneously. SpaceX goes a step further with Raptor. Both methane and LOX are subcooled, chilled below their boiling points to increase density. Subcooled methane packs more propellant mass into the same tank volume, boosting performance without requiring larger tanks. It's an elegant engineering move, but it also adds complexity to ground operations and in-flight management. Any thermal perturbation can cause the methane to begin boiling off, generating vapor pockets in the propellant feed lines. Vapor pockets in propellant lines are exactly what you don't want. Think of it this way. If a gas bubble enters a pressurized pipe, pressure in that line will spike sharply as the bubble moves through. In a rocket engine operating at hundreds of bar chamber pressure, a pressure spike from a vapor pocket can trigger combustion instability and, in extreme cases, engine failure. This is why thermal management of a methane rocket is significantly more complex than RP1, and why failure modes associated with methane engine cluster thermal management represent an area the industry is still actively learning. Property 3. Combustion instability at high chamber pressure is not yet fully characterized. This is the most critical technical point, and the one where we have to be honest about the limits of public information. Combustion instability occurs when the combustion process inside the chamber becomes temporally and spatially non-uniform. Instead of burning steadily and continuously, combustion fires in discrete pressure pulses at a specific frequency. If that pulse frequency aligns with the natural acoustic resonance frequency of the combustion chamber, the two phenomena amplify each other and can destroy an engine in milliseconds. Combustion instability has haunted rocket engineers since the 1960s. The F1 engine powering the Saturn V, the most powerful engine ever operationally flown at that time, required years of development and thousands of hours of testing to resolve combustion instability before certification. And that was on RP1. Raptor operates at approximately 300 bar chamber pressure, the highest of any operational rocket engine in history, per SpaceX published data. No engine has ever operated at that pressure for long enough to build a comprehensive database of methane combustion instability modes at that regime. Increasing chamber pressure changes flame speed, propellant residence time within the chamber, and the coupling between acoustic modes and combustion in ways that mathematical models can partially predict, but not fully. The specific combustion stability data for BE4 and Raptor is proprietary. These companies don't publish it, for entirely understandable competitive reasons. But the consequence is clear. The external technical community lacks sufficient data to fully assess failure risk for these engines at operational scale. Together, these three properties, distinct sloshing dynamics, more complex thermal management, and poorly characterized combustion instability at extreme chamber pressures, explain why RP1 engineering experience cannot simply be copy-pasted onto methane. And the flight heritage needed to truly understand these failure modes cannot be replaced by simulation, no matter how sophisticated. The twist: failure is data, and the industry is running short on it. Here's where I want you to stop and reframe the way you're thinking about this. When a rocket suffers an anomaly, whether it's an unplanned engine shutdown or, in the extreme case, a pad explosion, the natural community response is, "It failed. Who's responsible? When will they fix it?" Completely understandable. But it misses a critical truth about how knowledge is built in the rocket industry. Failure is not the opposite of progress. In many cases, failure is a prerequisite for it. Consider the test pilot programs of the 1940s and 50s. Engineers designing aircraft had no idea how a vehicle would behave approaching the sound barrier. They had theory, they had models, but the real behavior only emerged when pilots actually flew to that boundary, and not all of them survived. The data from those flights, including the crashes, is the foundation of modern aviation. Rocket engineering follows the same logic, with one critical constraint. You cannot deliberately manufacture a catastrophic failure to study it. Nobody launches a rocket intending to destroy it for data collection. That means every failure that occurs during development, as costly as it is the only full-scale, real conditions data point for that specific failure mode. SpaceX lost Amos 6 on the launch pad in September 2016. The cause: a COPV, composite overwrapped pressure vessel, containing helium inside the LOX tank, ruptured during propellant loading, triggering a cascade that destroyed the vehicle and payload in under a second. SpaceX spent roughly 4 months on investigation, COPV redesign, and system recertification. But the more important point: before Amos 6, nobody knew that a COPV in that configuration could fail that way under those specific liquid oxygen exposure conditions. No simulation had predicted that exact failure mode. The data from that event is what SpaceX and the broader industry used to deepen understanding of LOX and composite material interactions. The same applies to every major anomaly in rocket history. The Soviet N-1 exploded 4 times in succession between 1969 and 1972. The program was canceled, but the data from those 4 failures on combustion instability in large engine clusters and vibrational coupling across 30 NK-15 engines running simultaneously is still studied in aerospace engineering programs today. Ironically, the N-1 is the canonical case study for cascade failure in large clustered engine architectures. Now, when a catastrophic pad event occurs involving New Glenn, representing the first large methane engine cluster of its scale, what does the industry learn? Quite a lot. Per reporting from NASA, spaceflight.com, and Aviation Week, the U.S. Space Force maintains sensor arrays around launch complexes at Cape Canaveral as part of range safety infrastructure. In an event like this, those sensors capture overpressure wave data, thermal signatures, fragment trajectories, and event sequencing timelines with high precision. That is real data on how a large methane engine cluster fails on the pad, data that did not exist before, because no methane cluster of this scale had ever failed on a US launch pad. This doesn't mean failure is good. It isn't. It's expensive, it delays programs, and it has real consequences for mission timelines. But it also means the industry just received its first data point for a specific failure mode, and that data point will be analyzed, shared to some degree within the technical community, and will influence how future methane engine clusters are designed. Aerospace enthusiasts are asking, which engine failed? That's the right question for this week. The right question for the next 10 years is, what did the industry just learn? And how will that reshape the design of Raptor clusters? Neutron's REM-75 and Prometheus? Implications: what the methane era actually looks like in practice. So what does all of this mean for the real-world timeline of programs staked on methane engines? Looking at the current landscape, a clear pattern emerges. Nearly every major program this decade depends on methane engines maturing on schedule. Starship needs Raptor engines reliable enough to support NASA Artemis missions, landing astronauts on the Moon, and in the longer-term vision, Mars missions in the 2030s. Raptor is accumulating flight data faster than any other methane engine, but it remains in active development with significant design changes between versions. New Glenn needs BE-4 engines reliable enough to execute NASA lunar payload delivery missions, including the Blue Moon Mark 1 lander and lunar terrain vehicle delivery contracts. NASA's stated timeline for these missions runs 2027 to 2028. Rocket Lab's Neutron, powered by the REM-75 methane engine, is targeting the competitive medium-lift market against Falcon 9. Operational target, approximately 2026 to 2027. Ariane Group's Prometheus and the Themis demonstrator are building toward a reusable European rocket generation. Longer timeline, but still dependent on the methane engine knowledge base being built right now. All of these programs are racing on the same schedule, but methane flight heritage is accumulating at the pace of reality, not wishful thinking. This creates a tension that is important to watch. Is the industry moving faster than its own knowledge base allows? The honest answer, possibly. And that's not necessarily a mistake. Merlin took roughly 8 years from first flight, 2006, to reach the reliability level it holds today. Across those 8 years, there were failures, anomalies, missions that didn't quite reach target orbit, and had to deploy payloads lower than planned. Reliability isn't something you design into an engine. It's something you accumulate through experience, and experience only comes from flying. The issue isn't that methane engines are being developed too fast. The issue is that the programs depending on them have been planned under the assumption that methane engines will mature on schedule, and if that assumption proves wrong, the consequences aren't just a delay for one company. They cascade across every program in the stack. NASA learned this lesson once with Starliner. Never put all your eggs in one basket for crew transport. They were right to buy additional Crew Dragon missions as a backstop. The question now is whether that same lesson is being applied to methane engine dependencies within the lunar architecture. That's the question anyone tracking this industry should hold on to as they watch announcements about lunar missions and deep space architecture unfold in the years ahead. How many times has the Merlin 1D failed across its 400-plus missions? Per public data, there's at least one confirmed unplanned engine shutdown on a Falcon 9, and the vehicle still delivered payload to the correct orbit because Merlin was designed with sufficient redundancy for mission success even after losing an engine. That's not luck. That's the direct result of 400-plus missions accumulating enough data for engineers to know exactly how much margin the system needs to survive a single component failure. The question for the methane era: when will Raptor, BE-4, and their successors carry enough heritage for us to know, with that same level of confidence, not that they won't fail, but that we understand how they'll fail, and that the system carries enough margin to survive it? Merlin needed 8 years to become the engine the entire industry trusts. Methane engines are being asked to do it faster because of the moon base, because of Mars, because an entire generation of mission architecture is waiting behind them. That's not a reason for alarm. That's a reason to pay close attention. Every flight, every static fire, every anomaly in this phase is another page in the book the aerospace industry is writing on methane propulsion. And that book will determine the speed at which we actually expand beyond Earth. How many more flights do methane engines need before you'd trust them for crewed missions? drop your number, and the technical reasoning in the comments. I read all of them. If this kind of analysis is useful to you, subscribe to the Space Brief and check the video on screen for more.